Okay, this is Module 1B. We're going to talk about work and mechanical energy, and then we're going to talk about conservation of energy, which is the first law of thermodynamics. Get an introduction to that today. First of all, as you recall from physics, work is the integral of F dot dx. That's force through a distance in the direction that the force acts. So work actually is equal to the integral of F times dx times cosine of theta, where cosine of theta is the angle between the force and the direction it's acting. Now work depends on path, so the path that I push the device will affect the amount of work that's done. Again, we talk about work being a path function. If we do a force balance, then the resultant surface force plus the force of gravity is equal to mass times acceleration. That's Newton's second law. Remember, acceleration is dv dt. So m dv dt is force. If we look at the work to overcome gravity, then that's the integral of the force, mg times dz, z being the upward distance, is equal to mg times delta z. When we integrate that force and raise that weight, we have what we call potential energy. If we look at the work to accelerate, that's the integral of the force times dx, and dx being the velocity times dt, the distance being the velocity times dt. So the integral of m dv dt is the integral of mv dv, just rearranging that a little bit. And you have mv squared over 2 evaluated between the limits will be m delta v squared. And we call that kinetic energy. So the relative change in velocity squared is your kinetic energy. I'd like to look at this pole vaulting example and look at the conversion of mechanical energy. How many calories does it take to do one pole vault? How many calories of mechanical energy? I like to use this example. If I ate a Snickers bar, then how many pole vaults could I do? That's an example at the end. Now the truth is that all of your chemical energy in the Snickers bar can't be converted completely to mechanical energy. But if it could, and the body's really an amazing device in converting energy, if it could, how many pole vaults could you do? So at the end of when you do your homework for this module, I want you to go and find that out. So go and look at how many calories there are in a Snickers bar and convert that to energy and see how much potential energy you'd have. Another question I like to ask is, how fast do you have to be going? If you can run along, say the guy's running along toward the pole, with his pole and making the vault, how fast does he have to be going to reach a certain height? So go and look up the highest pole vault, and then go and look up the fastest, let's say 100-yard dash, and make a comparison of those two energies and see what you have. Kinetic energy of the 100-yard dash, potential energy of the pole vault. That's a good exercise for you. So one thing you should be aware of, that dietary calories are actually kilocalories, so be careful with that. Shaft work. In a shaft, if we have a shaft rotating, then we take the RPM times the torque, and we get the work out of that. 2 pi times the RPM times the torque. So you get 2 pi to get the radians, and the torque is actually foot-pounds. The radians are worked in there. For electrical work, those of you in electrical engineering, or everybody for that matter, should know a little bit about this. The power, recall, is the voltage times the current. Now we're looking at mechanical energy in this module, and those are all convertible completely between each other. I could take this work from a shaft rotating and turn it completely into electrical work, theoretically. Again, we talked in the last module about work being the force through a distance is also equal to the pressure times the volume. If a piston is expanding, or if a gas is expanding, its volume increases, the work done by the working fluid is equal to the pressure times dV. Now, one thing that I like to get into when we get into talking about the second law of thermo, which is the law of entropy and how friction works in and slows things down, is what do you have? Which pressure do you use when this gas is expanding? Well, if you look at this, we have the internal pressure trying to push up the piston, let's say, but you have friction here at the edges with the cylinder. So the external pressure being the load of the piston, the weight of the piston per area, plus the pressure of the atmosphere, this internal pressure has to be actually greater than what I call the external pressure. The reason being is that it has to overcome a little bit of friction. So the work that you receive in pushing back the atmosphere and raising the piston is less than the work that's actually done by the gas, because it has to use this P internal to do its work. If P internal equals P internal, then of course nothing happens. In fact, to accelerate the piston or to move it at all, P internal has to be greater. But even if you're moving at constant velocity, there'll be some friction there, and P internal will have to be greater. Take a look at this a little more carefully. If P internal is greater than P external, then the work internal is the integral of P internal dV. That's the work done by the working fluid. But the work external received by the surroundings is P external dV, and that's always less because you had to overcome friction. The remainder of it is lost. P internal minus P external dV is lost. So that's irreversibility, and that's the first time you're hearing about irreversibility, but that really goes to the second law of thermodynamics, which says that you always lose a little bit. Something is dissipated in everything you do. We call that an irreversibility, and we'll have a module later on irreversibility. It cannot be recovered, and so that's really lost forever. Any process has some dissipation to it. In order to estimate work to and from the surroundings, we'll let P internal equal P external. We'll let that represent a quasi-equilibrium or a quasi-static process. Now remember, if the internal pressure is the same as the internal pressure, then the piston won't move. To make things happen, you have to have a gradient. You have to have something pushing it, a gradient in pressure, so that the internal pressure overcomes the friction and overcomes the external pressure in order to move. Same is true with heat transfer situations where heat is moving from one place to another. If T internal equals T external, if we have no gradients, nothing will happen. If there are no gradients, nothing will happen, and we call that a quasi-equilibrium, or often called a quasi-static process. Now, equilibrium means there's no change in the properties with respect to distance. And if there's equilibrium, there's no driving force to make things happen, and so nothing happens, and we call that a quasi-static process. Here we're talking about thermodynamics, but we often approach thermodynamics by looking at thermostatics, or when things are just about to happen but aren't quite. Okay, when we're integrating PDV, the path matters, the process matters. So some processes that we could consider are, for instance, it goes along the path where it's an ideal gas and PV is constant. We can also have a process where PV to the K is constant. We call that a polytropic process. We can have an isobaric process where P is constant. Now we're specifying things about the path. Along the path, in the case of the isobaric process, we're keeping the pressure constant, and so that specifies the path, and we'll have a different result depending on the path that we take in terms of the amount of work that's done, work being a path function. Okay, if we look at a spring, force is equal to K times X, and if this specifies what's happening along the path, force equals K times X, K being the spring constant, then work is equal to the integral of F dx equals integral of kx dx, and you get this result, kx squared over 2, evaluated between the limits. So there's an example of a path type function. Now I want to look at the conservation of energy, which is the first law of thermo. First law of thermo says that energy is conserved. It can't be created or destroyed. Now that's not completely true. You know that mass can be converted to energy, but within this course we're not going to be looking at that. You remember the famous equation E equals mc squared. We won't be looking at nuclear reactions in this course. So we'll be saying that energy cannot be created, cannot be destroyed, so we can do an energy balance. And this concept of a balance is something that you'll use over and over again. It's basically the way you balance your checkbook. What goes in either goes out, or the balance goes up and down, meaning it's accumulated or stored in your account. In equals out plus accumulated. My favorite equation. Closed system. If we start looking at closed systems, a closed system is defined as one where the mass does not go in or out of the system. There's no mass in or out of the system. However, work can go in or out, so you can have the energy of the system can be influenced by how much work I put in, how much heat I put in, or how much work or heat I take out. Again, there's no mass bringing in any energy into the system, so the energy changes only because of Q or W. If I do a balance on that, and in this system, the way I've drawn the arrows, and when you're working your problems, there's a lot of methods. The book will give you one way, I'll give you another way. My way is to draw arrows on the system. Make a careful drawing of the system, make an estimation in your mind of whether work is going in or out, whether the heat is going in or out, and draw your arrows. From your arrows, you just follow along and do your balance. Write the equation in equals out plus accumulated. And so since my arrows are both going in, I have work going in, heat going in. So you'll have delta E, the change in energy of the system. In this case, if I truly got it right and work and heat are both going in, delta E will be positive. Sometimes I'll work a problem and I'll find that the work, if I calculate work from this equation, it comes out negative. What's that mean? That means that the work was really going out of the system rather than going in. We can write this, if we use small letters, then we're talking about the work per mass. So throughout these modules you'll find the work, if I write it with a small letter, I mean per mass. So it's, we call it a specific work, but it's, let's just say a work per mass of the system. And Q is work per mass, and delta E would be the change in the energy of the system per mass. Now this is a property. Delta E will be property of the mass. So the small letter is a specific property. Another thing that you can do is you can do this whole thing on a time basis. In other words, as a flow per time. My nomenclature is such that whenever you see a dot, that means a flow. That means per time. So work per time coming in, or a flow of work into the system. Now what would a flow of work be? Work has units of kilojoules. So the flow of work would be kilojoules per second. Remember, kilojoules per second would be kilowatts. So kilojoules per second coming in would be equal to a change in energy, or a rate of change of the energy of the system. So dE dt would be kilojoules per second, or kilowatts changing. But really you're looking at a reflection of that. How would you know that the energy of the system is changing? Well, you put a temperature sensor on it, or you'd watch the volume change, perhaps. There are a number of ways, and when we go into properties, we'll find how to track the energy from various things that we can measure, like temperature, or volume, or pressure. Okay, here we have a system that has adiabatic walls. First time you've heard the word adiabatic, and you'll hear it again and again and again. Adiabatic means no heat transfer. So what I'm saying is there's no heat transferred out of the system. Q is equal to 0. Q dot, the flow of heat out of the system, is equal to 0. Now, how do we make something adiabatic? We put a whole lot of insulation around it. If I want this to be adiabatic, I have to have perfectly insulated so that no heat can get out of this system. If the system is air, if we treat the system as the air in the room, let's say, of course we have people in there too. By the way, these people are putting out a little heat of their own. Go and calculate how much heat a typical person puts out and base that on a 2,000 calorie diet. I think you'll be interested in the result. Do that. Go and find out for a 2,000 calorie diet how much heat you're putting out on a continuous basis on average. So you can get it to heat per day, you can get it to heat per second. Go ahead and get it in watts and find out how much a typical person puts out. And then say we have this work coming in from the room. The work, so the people are putting off heat. There's work coming in from the light socket, going to the light, putting out energy there. Then dE dt would be equal to the heat of the people plus the heat plus the work coming in from the electrical socket. That will give you your change of energy in the room, and that would be reflected by an increase in temperature. Okay, I want to talk a little bit about heat transfer. It's important that you know this because it gives you a feel of how heat is moving. Heat transfer is defined as the movement of energy from one place to another because of a temperature difference. Now, there are three modes of heat transfer: conduction, and conduction is when the temperature changes dt. Conduction, this is Fourier's law. Q is proportional to K. K is the thermal conductivity times the area. The more the area, the more heat is going to conduct. And this is the cross-sectional area perpendicular to the direction of the conduction. Times dt dx. Now dx is in the direction of the heat transfer. So this is a gradient. Okay, and again we talked about gradients making things happen. When I have a gradient in temperature, say it's very hot on one side of the wall and very cold on the other, then you'll have a large amount of heat transfer through that wall. The thinner the wall, the smaller dx, the higher the rate of heat transfer. So that would be a higher gradient. A higher gradient because a short distance and a high temperature drop give you a very large gradient. That times the surface area of the wall, so you have a large wall, will give you a lot of heat transfer. Obviously, the bigger the wall, the more heat's transferred. K is the thermal conductivity, so something like copper, which has a K of about 400 watts per meter degrees C, would have a much higher rate of heat transfer than glass or air, if you could get stagnant air, which has a very, very low K, or thermal conductivity. Convection, we describe that with a heat transfer coefficient we call H. And H depends on the wind speed or the speed of the fluid flowing by a wall. Convection is when heat is picked up by a flowing stream near to a surface, and the heat is pulled off the surface by the flowing stream. So obviously a very fast stream will move the heat away fast. A very slow or almost stagnant stream of air will move the heat away very slow. So this, again, you have a temperature difference. This is the temperature of the wall. T infinity represents the temperature of the medium, or the air, let's say, that's flowing by the wall. Finally, a third mode of heat transfer is radiation. And radiation actually does not require any medium to transmit heat. Radiation flows on a wave, and so you can actually cool a great deal, especially on a clear night, because you're radiating out to space. The temperature difference is also to the fourth power, so that's the temperature of the surface to the fourth minus the temperature of another surface far away to the fourth. So if you're radiating out to space, it's very, very cold out there. Let's say 0 degrees Kelvin. So you have a very large rate of heat transfer when there's nothing in the way, and you're radiating all the way out into space. This can freeze your plants in the wintertime, so if you want to protect your plants, you put them under a tree or put a cover over them so that they're radiating out to the tree. And the tree will be, say it's cold and it freezes, the tree will only be 32 degrees Fahrenheit, which would be, shoot, that's almost 500 degrees Rankine. And so that's a relatively high temperature compared to space, which is 0 degrees. And you'll really slow the amount of radiation you're losing from your plants, and often frost won't form if you cover them up or put them under a tree. You can protect your plants to a great deal by doing that. So radiation is another mode of heat transfer. This little thing is called the emissivity, and things that have a high emissivity are black surfaces. Low emissivity would be things like shiny objects. So I don't want to get too deep into that, but that's radiation. This sigma is Boltzmann's constant, and it's just a number that multiplies this whole thing to give you actually the Q that's lost by radiation. So that's a net heat loss between two surfaces. Okay, now we're going to talk about energy stored by mass. First of all, I want to look at macroscopic. If I take a chunk of matter, not looking inside at the molecular motion of the particles, of the molecules, but looking at, say, a rock flying through the air. It can have potential energy if I raise it up to a higher height, or have kinetic energy. Then we're going to look at microscopic. Microscopic molecular energy is internal energy, and we get pretty deep into this in thermo, not deep into the motion of the molecules. We're not going to get into how this occurs. We're going to find out how we can follow the internal energy from various other properties such as temperature and pressure. Internal energy, U. That's the symbol given to it. Finally, another form of energy, going back to what finally we're going to review a little bit. So work is a path function. It's a mechanical or electrical form of energy. Work is high quality energy, and I alluded to that earlier. Basically because you can convert work into heat completely, but you can't completely convert heat into work. Then we looked at the conservation of energy, and energy may have to be accounted for. In fact, that's really what the first law of thermodynamics allows you to do. It gives you an equation, an energy balance equation, that allows you to calculate different things on a system. It's one equation, so with that one equation you can solve for one thing. Energy may be stored, and we're going to store it typically in a mass, either in a mechanical, macroscopic sort of way by raising the height of the mass or by speeding up the mass, or in a microscopic way by raising its temperature or changing other properties of the material. Finally, we can have energy entering and exiting with the mass, entering or exiting your system, or with heat or work. So that's pretty much a summary of an introduction to energy. We had an introduction in the first module, or module 1A, of general physics concepts that I want you to go back and review. And then go take a look at this work. First of all, read chapter 3. Read all through it. It has a lot of good things in there, including a little section on heat transfer. And I want to work these problems, which are really focusing on some of the things we just talked about. If you get to problems 130 through 139, I think in every chapter you should try to work these, what we call FE review problems. Eventually you're going to need to take the Fundamentals of Engineering exam. Those are multiple choice tests. And it's probably a good idea, because I'm going to have to give you multiple choice quizzes. So it's probably a good idea to just get in the habit of being able to quickly do those multiple choice type problems. So as you're going through, in fact while I'm at it, as you're going through all of your courses, it's probably a good idea to set aside some time to study. Try to work any multiple choice type questions you have. Personally, I like to give tests where you can get partial credit, because a small mistake can lead to when you're in a hurry can throw you way off when you really may have understood the concept. However, a lot of times you'll have to take multiple choice tests, and one of those is Fundamentals of Engineering exam. And one of my goals is to have every one of you pass the Fundamentals of Engineering exam and become a professional engineer. So in this course and in all your courses, I recommend that you study, put that aside somewhere in a folder, and when you get through all your courses and are ready to take the FE exam, you can pull that back out and review it. Okay, so this is the end of this module. Have a good day.